Greetings. So in quantum mechanics we have learned so far that position and momentum, or in some sense position and velocity, cannot be determined simultaneously, and this is an automatic consequence of quantization, that we cannot really the whole issue boils down to the limitations on the process of measurement. So it's not because of any inaccuracy in the experimental method, but in the very act of measurement, there is some information that is lost. And a classic view of this can be obtained from the Young's double slit experiment, and we will discuss that. So Young was a brilliant person who is often considered as the last person who knew everything. And he conceived, he set up this experiment, which is a classic experiment, and this is a figure from a simulation by our friend Uday. He has simulated the Young's double slit experiment, and there are some other things also involved in this simulation about which I will talk as we discuss further. But essentially you have got a source of either light or particles. It can be an electron gun, which can go through two slits, and it has the possibility of going through either slit 1 or slit 2, but both the possibilities are open, and when you have both the possibilities you get an interference pattern. Now what is interesting is that you account for this interference pattern in the traditional explanation of the Young's double slit experiment by invoking the wave description, and then the intensity itself, which is a measure of the probability. It gives you information about where the particles are likely to arrive. So there is a wave particle duality that is getting built into our vocabulary. Okay? So you are using the wave amplitudes, all right, to construct the superposition, but that is giving you a measure of the intensity of the fringes. All right? Okay? And that is where you find the particle to arrive, and there again you are talking about particles. So what is interesting about this experiment is that you see the wave particle duality, and there is a lot of talk about is this a wave or is it a particle, and what is it? And one nice term that I found on the internet, some student of physics has written that he would call it as a golf ball. In Dutch the meaning of golf is a wave, and he came up with this term called golf ball. I think it's a nice term. And what is exciting is that you see the interference pattern even when there is only one particle or one photon in that apparatus. Now this is really stunning. Okay? And then if you perform a which way experiment, if you try to find out from which particular slit the particle has gone, then the interference disappears. So when you perform an experiment in which you have some mechanism to know from which slit it has gone, the particle has gone, and you can do it easily by simply putting a shutter on one, and then you know that okay, it has obviously not gone through this slit where you have the shutter, then obviously it has gone from the other. So this is a simple one's which way experiment. So such experiments are called as which way experiments. And when you perform a which way experiment, then the interference is destroyed. And this happens even when there is a single particle or a single photon in the whole apparatus. Now, I won't worry too much about what is the technology to develop single photons and how to detect single photons and so on. So, that is something which I will let you read up. But I will give you a few references which will remove any doubt from you that yes, you can actually do these experiments with single particles. So, let me give you these references over here where you deal with just one particle at a time. So, here is a reference to a paper, a single photon source that you can make at home, all right. Then here is another reference, direct detection of a single photon by human eyes, all right. So, here is another reference in Nature Communications just few years ago, all right. So, look it up, and then there is another nice paper in the American Journal of Physics on Young's double slit experiment with single photons and quantum eraser that I will suggest that you read up, all right. So, that will remove any doubt from your mind that okay, such experiments can in fact be done, they have been done. What is remarkable is that such experiments were not done when Feynman gave his lectures in the early 60s. And Feynman points out that this is this experiment really has the heart of quantum mechanics, that everything that is there in quantum mechanics is contained, all the shock is there in the Young's double slit experiment, and at a fundamental level there is no more principle that is involved in quantum mechanics which is not there in the Young's double slit experiment. So, it is really it's regarded as one of the most beautiful experiments in physics, and it's really something that you should think over again and again, even if you are familiar with it. So, this figure is again from Uday's simulation, and he subsequently goes on to do a simulation of the Aharonov-Bohm effect and the Berry phase, which I will talk about later. So, this is a double slit experiment, and you have a source of light, or it can also be a source of electrons, all right. And then the two slits are open and you have an interference pattern, all right. So, this is what you have when both the slits are open. So, I will not explain the figures very much, they are self-explanatory and you are familiar with this from your previous courses. So, this is the interference pattern that you get. Now, you can do a which way experiment. So, you can have shutters, those purple sticks are shutters. You can shut one or the other, or shut both and go home, all right. But when you have both the shutters open, then you have the interference pattern. But if you perform a which way experiment that only one of the shutter is open, then the interference pattern is lost and you get the classical distribution of intensity, which is a single peak in front of the open slit. That is what you get, all right. Now, you can do this which way experiment in different ways. You can have both the slits open and put polarizers, okay. And these are polarizers at which are orthogonal to each other. So, you know that the light which is coming out of them is polarized in only one way, all right, and not the other. So, again both the shutters are open, but you have means to know from which slit the light has come through. It has, the light which reaches the detector has come through either the vertical polarizer or the horizontal polarizer, and again you have the information with you that the path that light has taken before it lands at the detector. So, again the interference pattern is lost. Now, what you erase this information? There is some information with you and you forget about it, and you forget about it by erasing it, all right, you take an eraser and remove that information from your book of knowledge, all right. So, how can you erase it? You have a third polarizer, okay, and the light coming out of the third polarizer, which is the eraser, will be polarized in the direction in which this third polarizer allows the light to go, right, and whatever information you had is now gone, right, and the interference pattern reappears. So, once again you have got these dark and bright fringes. Now, this is amazing, all right. Now, see how you are going to deal with this information and lack of it. So, you acquire an information, but then you lose that information, but here you have lost the information before light has reached the detector. What if you choose to lose that information later, after light has reached the information, the detector, all right? Can you do that? So, sure enough you can do that. You can shine the two slits by some source of light, and light is scattered, and the light is scattered and you can detect the scattered light, and from this you sort of peek into the experiment. You peek into the experiment and say that, okay, now I know that light has come from slit 1 or slit 2, and let me see if there is interference, and the interference is lost. The moment you get that information, all right, but suppose you erase this information. So, how can you erase this information? You can put a lens, all right, and now you do not know from which slit the scattered light has come. So, the information is gone and the interference fringes reappear, all right. So, they seem to know what kind of experiment you are doing, all right. So, this is amazing, and now what you can do is keep this eraser far away. This is called as a delayed choice eraser, okay. You can put this lens like a billion kilometers away when the detector is at a distance of a few centimeters or a meter or whatever, all right. And now what is going to happen? Because you are going to detect this, okay, after the particles have actually hit the screen, and the information that you potentially can get is erased at a later time. So, this is the delayed choice quantum eraser, and the interference pattern pops up. And we know very well that information does not travel at a speed faster than light. We know that no particle travels at a speed faster than light, and whether you have an electron gun or light itself going through the two slits, it is not going to go faster than the speed of light, and you are keeping this detector a billion kilometers away or even a few light years away. But if you have that in the apparatus, then the information is lost, okay, and the interference pattern pops up again. Now, this is why Feynman says that this is such a remarkable experiment. It has got the heart of quantum mechanics. Everything that is, it's so mind-boggling that just the presence of the possibility of detection, okay, destroys the interference, but erasing it any time, even after you think the particles would have reached the detector, restores the interference. Now, this is what makes quantum mechanics so mind-boggling. Okay? So, here is a nice paper which I would like to recommend on the Slit experiment, all right. And what the quantum eraser does is it erases this information, even if it is a delayed choice kept far away from the apparatus. You have to deal with this mind-boggling situation knowing that superluminal messages are not possible, but somehow the quantum eraser erases this information and the interference fringes are restored. Okay? So, this is similar to what we discussed earlier in the context of another Young type experiment, similar in principle, although different in details, which was the Stern-Gerlach apparatus. Okay? And in this, you pass silver atoms through a magnetic field, all right, and then you have the two components. We have discussed this experiment in an earlier lecture in this course. So, you have a shaped magnet, and what it does is it separates the incoming silver atoms into two, it splits it into two, because the silver atom is a neutral atom, but outside it has got an uncoupled electron. So, it has got a net angular momentum, and this net angular momentum, which is an intrinsic angular momentum, it is spin half, and it has got two components along the z axis, the plus and the minus, and these are the two components which separate out, which is very surprising, because classically you would have expected only one peak, but now we observe two, and this is very nicely explained in Sakurai's book. So, we also discussed the sequential Stern-Gerlach experiment, in which you have got a magnetic field along the z axis, then you stop the component along the minus, right, the spin minus components you stop, allow the spin up components to pass through another Stern-Gerlach apparatus, again with the z axis along which the magnetic field has got is along the z axis, then again you get the same. So, if you perform repeated measurement on a prepared state, on a pure state, then you keep getting the same result again and again, no matter how many times you perform it. But if you have a Stern-Gerlach apparatus in which the magnetic field is along the z axis, stop the minus component, the spin down component, and go let the spin up component go through a different magnetic field, a Stern-Gerlach apparatus, which is oriented at 90 degrees with respect to the previous one, then you get two beams, but one with spin down and the other with spin up with respect to the x axis. And then if you perform, you stop the one which is along the spin down and take only one of these and let it go through a Stern-Gerlach apparatus along the z axis, which is the same as this, you recover the minus component over here. Now, this is astonishing because you stopped it here, and it is only the plus component which was moving from left to right in this figure, and having stopped the minus component over here completely, what is remarkable is that you recover the minus component over here. So, these are the astonishing parts of quantum mechanics, and it comes because of a fundamental idea in quantum mechanics, which was introduced by Schrödinger himself. He talked about entanglement, which generates the possibility of having a cat which is both dead and alive. This has baffled some of the most brilliant minds in physics. Bohr said that if quantum mechanics has not profoundly shocked you, then you have not understood it. And Feynman says that nobody understands quantum mechanics. It's somewhat consoling, but also challenging. So, this is what happens. If both the slits are accessible for passage, then the system wave function is a superposition of these two, all right. So, it is 1 over root 2 of one plus 1 over root 2 of the other. Now, what is the amplitude of the electric vector? Suppose you are carrying out this experiment with light. The amplitude of the electric vector at the detector is the sum of the two amplitudes. So, this is just the superposition of waves, right. And if you look at the Poynting vector, okay, it has got a magnitude which is 1 over mu 0 times E b or C epsilon 0 E square. And then if you determine this, then you see that from the cross term E1 dot E2, you have the possibility of in phase or out of phase scalar product, okay, because the cosine theta depending on the phase angle of the two waves, all right. This can go anywhere from +1 to -1, okay, and this is what generates the interference pattern. Now, what the which way experiment does is it determines, it expands the Hilbert space. So, now you have a marker, the which way marker, all right, whose states in the vector space are denoted by states m1 and m2. So, these are the marker, and the state vector is now to be represented in this expanded Hilbert space along with the marker states, and the marker 1 and 2 are obviously orthogonal to each other, which is why they are markers. Okay, the marker is going to tell you, it is going to mark from which slit the particle has come, and it could be any one of the previous. You can have a shutter, you can have polarizers, right. Just the fact that you have got these markers are orthogonal to each other, and what they do is they are allowing you the opportunity to peek into the apparatus. Okay? If you open your eyes and you peek, you use this marker, then you will know from which slit it has come, and just the presence of this marker has this orthogonality. This is what destroys the interference. It does not matter whether you carry out the delayed choice experiment, because the state vector itself has got the marker states built in. Okay. So, these are some of the fundamental ideas in quantum mechanics which makes it so baffling. You can represent a state function, okay, by a Fourier superposition of various momentum states, okay, and the complete Fourier representation will require this infinite sum or limit of a sum, which is this integral that we have on the screen, right. But typically you would want to work with wave packets in which there are a few momentum states, and these few momentum states, let us say that they are spread over a momentum range of delta k in units of h cross, okay, h cross k is the momentum. So, You may have even in vacuum a dispersion, and you can write it if you like an infinite series, but even if you take a few terms you can get the physics out, all right. And if you write the k dependent omega in the wave packet description, right, it is the same term, there is nothing new in this. So, do not be bothered by how quickly this whole equation pops up on the screen. It takes a while to write it on the board using a chalk, but it takes just half a moment, less than that, for it to pop up on the slide. And that gives you some advantage, because the concept is simple and you do not have to worry about the expansions and the derivative and where the derivative is taken and so on. All that is something that you know very easily. You have been working with these derivatives for the past 4, 5, 6 years, right. So, you are very comfortable with that. Just a glance at this equation tells you exactly what is going on. So, there is a definite advantage in using these pop-ups. You can pay attention on the main concept in physics which we are talking about. So, those of you who are still used to chalk and board education will see that this is actually an advantageous, it is a huge advantage to use technology so that we can concentrate on the physics concepts. So, there is nothing in this, all right. I have only mere substitution which a schoolboy can do, right. Again, there is nothing in this, it is the same equation which is rewritten, except that it is multiplied and divided by e to the I k 0x, right. Rewriting it on the board would take time, but there is nothing more in it. Okay. And now you can see that this is a wave whose amplitude is A tilde, okay, A with that wiggle which is called as A tilde, and this A tilde itself does not have a single component of momentum, but it has got a number of them. Okay. You have a large number of waves with different momenta which are packed into this. And it is this wave packet which is moving at a group velocity d omega by dk. Okay. The peak of the wave packet moves at this group velocity. So, this is what is getting into the uncertainty principle. So, you see that this feature is already built into the Fourier methods. This is coming straight out of Fourier methods, right. On this slide, we have not used quantum mechanics anywhere. This is just Fourier representation of a function, okay. So, it is already built into this, and the wave packet is not localized at a particular point on the x axis, it is actually spread over delta x, all right. And there is a reciprocal relationship between this, because the more you want to localize it, the more number of waves you will need. You will actually need infinite, all right. So, there is a reciprocal relationship between this, but what the Heisenberg uncertainty principle tells you is that what are exactly these inequalities, and that is where quantum theory comes in, okay. So, you can see this from the point of view of what is called as a Heisenberg microscope, which I will briefly discuss. You can see that to localize a particle, you need to superpose a large number of monochromatic waves, different momenta, right. And the more waves of different momenta you combine, the easier it is getting for you to localize the particle. So, this is complementary information. You have more information about the one, you lose information about the other, either which way. Okay? And then this is what manifests in quantum mechanics as the uncertainty principle, because you have to abandon this idea of representing the state of a system by position and momentum. They are complementary, so you cannot do it by position and momentum. You get one, you forget the other. Or if you want to get both, yes, you can get information about the both, but not with infinite accuracy. Okay? And the limits of that accuracy are contained in the uncertainty principle. So, this idea we will discuss further maybe after a few classes, when we also discuss the Feynman's path integral approach to quantum mechanics. It becomes very interesting, because now you are asking which way the particle went, how did it go that far and come back, and then the information reaches the detector and the interference pattern is right, and in the delayed choice the eraser can be very far away from the primary apparatus, but that is, no matter how far away, it is an integral part of the apparatus wherever you kept it. So, the particle has the possibility of taking infinite number of paths, and all of these paths are in principle possible acceptable paths, and how they interfere with each other is finally what leads to the observations. So, everything that can happen does happen. So, that is the title of a book by Brian Cox, which you might enjoy, and that also tells you why classical mechanics works where it does. So, you are superposing these complex amplitudes. So, let us consider two complex numbers, a plus ib and c plus id. All right. You take the modulus square. Again, it takes a while to write on the board, but you need half a glance to do this, and you know what it is, right? No big deal. And notice that if you take the real part of this product Z1 star Z2, it has got these cross terms AC and BD. Okay? And the fact that the wave function must be complex is therefore an integral part of seeing this interference pattern. Okay? The wave function in general therefore has to be a complex function. So, you have to deal with complex functions, because there is nothing complex about it. It's a real number a plus square root of minus 1 times b, but the imaginary part b is as real as the real part a. Okay, both are real. What you are doing is, there is nothing, no imaginary mathematics. You are handling two real numbers at the same time, and that helps you deal with the phase and the amplitude of the wave function. Okay? So, a complex function you can write as a plus ib, or you can write it as rho into e to the power I theta, if you like, in polar coordinates. And rho and phi, rho is the amplitude, phi is the phase, and you are able to deal with rho and phi together. And what generates the interference pattern is not just the amplitude, but also the phase, the cosine phi plus the I sin phi, right. The cosine terms are oscillatory, and when you have these oscillatory waves from two different sources, how they superpose will generate the interference pattern. Okay? So, you work with complex wave functions. So, wave functions in wave mechanics are in general complex functions. So, here let us do an experiment to see where an electron is. So, let us say a particle or an electron, it can be the electron, it can be something else as well. You shine light on it, all right, to see where it is. And of course, you must see the scattered light through a microscope. So, this is the lens of the microscope. It will have a certain aperture and a certain diameter from B to F, okay, and you must see it through this microscope to see where the particle is. So, that is the experiment you are carrying out, okay. And to see it with clarity, you keep it at a focal length, right, from this, so that you can see the light clearly, all right. Then you have got the energy of the photon and its momentum, which is P equal to h over lambda, and energy of course given by my initials Pc, right. So, this is the experiment you are doing. Now, where in the microscope are you going to see it? You might see it in the direction of F or in the direction of B, okay. If you see the scattered light in the direction of F, then you have minimum momentum transfer, or else you have maximum momentum transfer, but you cannot see it if there is no momentum transfer, okay. That is something that you have no choice with that. You can reduce it, but you cannot eliminate it. So, depending on whether you see it in the direction of F or B, it will have a different momentum, which is either Pf or Pb, and P being h over lambda, you have the two possible wavelengths, lambda f and lambda b, and lambda b will be much greater than lambda f, depending on the minimum momentum transfer and the maximum momentum transfer, right. So, momentum and wavelength have reciprocal relationship. So, let us consider observing the scattered photon in the direction f, in which case the scattered photon goes with a momentum p prime, which is h over lambda prime, right, and it comes at an angle theta with respect to the line joining the point D, and pi by 2 minus theta with respect to the line of incidence of the incident photon. So, you can write the conservation of momentum and get the momentum for the electron, the scattered electron. You can do this for the other possibility also, right. And notice that in the momentum conservation, you have got h over lambda prime, whereas over here you have h over lambda double prime. These are two different wavelengths because of the possibility of two different momentum transfers, and you also have a plus sine theta in one and the minus sine theta in the other. So, keep track of this sign, okay. Now, if you want the uncertainty in the momentum to be minimized, then what is desirable? It is desirable that theta min is almost equal to theta max, and lambda prime is nearly equal to lambda double prime, and then you do not need the primes anymore. So, you can just put a single lambda, right. This is what you will desire, and you will try to get this to reduce the uncertainty in the momentum. So, now let us see what it does. So, the least momentum gained by the scattered electron is me times Vx prime, and the most is me times Vx double prime. So, there are these prime and double prime that we are using, right. So, the most momentum gained by the scattered electron is this, right. Very simple idea, there is nothing very complex. So, the range of momentum that the scattered electron would have will be h over lambda times 1 plus or minus theta, because you are narrowing down theta as much as possible. So, this is a small angle and you may approximate sin theta to theta in this approximation, right. And this is the minimum uncertainty, and if you want to reduce it further, you are going to have to make lambda large, because you see that it goes as 1 over lambda. And the more lambda you use, the longer wavelength light you use, the uncertainty in the position would increase. So, the less the uncertainty in the momentum, the more the uncertainty in position. Okay? Right? So, delta p is 2h over lambda theta. So, just remember this relation, that delta p goes as the inverse lambda. Okay? So, there is a momentum uncertainty. The momentum uncertainty is 1 over lambda, and if you want to reduce it, you need a larger wavelength photon and then lose information about the position. So, let us see what kind of compromise you can make on this. All right. What is the resolving power of a microscope? Now, this goes as 1 over d. So, this, if you know the focal length, and you have this relation d equal to lambda over sine theta, or theta equal to lambda over d for small angles. Okay? So, we will use this relation now, because we will try to minimize the position uncertainty. So, the location of the electron can at best be placed between minus f tan theta and plus f tan theta, which are the two extreme points of the lens, right, because the electron is at the focal length of the lens, right. So, half the diameter on each side. So, you can see only either from half the diameter on each side, one side or the other. So, the location of the electron can at best be placed between minus f tan theta and plus f tan theta, right. So, from geometry you see that f over d is 1 over 2 theta for small angles. Sin theta is nearly equal to theta, tan theta is also nearly equal to theta, cosine theta is nearly equal to 1, right. And from the previous slide we have theta equal to lambda over d. So, we can put the two relations together and get the position uncertainty to be of the order of 2f times lambda over d. Okay? And what is f over d? F over d is 1 over 2 theta. So, you get delta x equal to lambda over theta. So, we had the momentum uncertainty, which was 2h over lambda. We have the position uncertainty, which is lambda over theta. And if you take the product of delta x and delta p, it is of the order of h. So, this is the Heisenberg, this thing. Now, this gives you order of magnitude estimates. So, this is not the exact uncertainty principle. The exact uncertainty principle is what we have already discussed. But you see that these order of magnitude estimates are, you cannot do anything with. So, you have the position and uncertainty measurements are not compatible with each other, which is why they are represented by operators which do not commute. But two momentum operators, they do commute. You can measure two orthogonal components of the momentum without any problem, right. The reason is the generators for these, the momentum being the generator of infinitesimal displacement. So, momentum is the generator of displacements, right. We have considered that. Even in classical mechanics, we have seen that linear momentum is conserved in homogeneous space due to translational invariance, because momentum is the generator of these translations, right. And the two generators which are orthogonal to each other, they commute. So, if you are going from home to your school, it does not matter if you first go east and then north, or you first go north and then east, it does not matter. So, these two commute. Okay? And as a result of this, the linear momentum operators commute with each other, but they do not commute with the measurement of position itself. So, I will stop here today's class, and we will continue from here in the next class, because we will talk about why the generators for linear displacements commute. So, they give you an abelian algebra, but when you work with rotations, you get a non-abelian algebra, then you do not have commutation. Thank you. If there is any quick question, I can take it.
Here we consider two or more waves having different wavelengths combined to get a wave packet. So, what would be the wavelength of that wave packet? It would be.
Yeah, I mean, it travels with a group velocity and it has got a certain spread.
In that itself, it have a
Yeah.
so smallest.
Yeah, so it has got a certain spread. It is there in the expression for the Fourier transform. So, it depends on how many momenta you have superposed.